In this video, I'm going to talk about wellbore breakouts. The first thing that we're going to do is we're going to revisit what are the stresses around a wellbore when we have an asymmetric state of stress. That means that one of the stresses, for example in this case SH max, is larger than the other principal stress in perpendicular direction in the plane perpendicular to the wellbore. So this is the cross section of a wellbore. Here's the rock, here's the wellbore. We have the stresses that we have said before. Also, we have a pore pressure in the rock, and inside the wellbore we have the wellbore pressure and a well-developed mud cake. As a result of the application of all these stresses, we're going to have hoop stresses, sigma theta theta, and radial stresses, sigma RR, that are going to vary around the wellbore. And for breakouts, we're going to be interested in calculating the stresses which are located at the points in which we have the maximum compression stress. As we can see from this plot, this is going to be in this location where hoop stress is at its maximum, and according to this plot, it's going to be at an angle of 90 degrees from the line of the maximum stress. So for example, in this example, opposed to what I have in this figure, I have the angle theta that is going to go from the line of the maximum stress, which in this case is this line, and to a particular point. For example, let me do this with another color. If I were to take a look at the stresses at the position somewhere over here, the angle theta would be this one. The distance r would be the distance to the location from the center up to this point, and in the direction perpendicular to the radius, I have the hoop stress. On the direction of the radius, I have the radial stress. I know in this case I'm also going to have some shear stresses, which I'm not going to put the name, but I just will draw very quickly over here. But remember, the angle theta is going to be the angle from the line that coincides with the maximum stress with the particular point we're looking at. So in this particular case, we will expect to have the maximum stress located at 90 degrees and at 270 degrees. These locations are going to be, therefore, right here and right there. All right, so if we take the equations from Kirch and we replace r, the radius for the wall of the wellbore, and if we take the angle as 90 degrees, the angle theta 90 degrees and 270, we're going to get these simplified equations of the hoop stress and the radial stress. Notice that the hoop stress is going to be larger than the radial stress, and is going to depend on the effective radial stress support, PW minus PP, but also depends on the asymmetry or the difference between the horizontal stresses. This is captured in this plot by this variation. What we can do now is we can use the equation of shear strength, which is sigma 1 maximum is going to depend on the value of sigma 3, but also on the value of UCS. Let me write UCS first. It's going to be the unconfined compression strength plus sigma 3 times Q. If I, in this case, take as sigma 3 the radial stress at this point and sigma 1 to be the hoop stress, this is going to translate in these equations as this. And if I use the equation of shear strength, where now this is my sigma 1, all of these between brackets, and this is my sigma 3, which is effective radial support, then I can equate for what is going to be the wellbore pressure for a given state of stress, for a given pore pressure, and for given properties of the rock UCS and Q, such that I have shear failure. And this is the equation that you have right here. This is a solution. This is going to be the wellbore pressure given the stress and pore pressure conditions and the properties of the rock at which I'm going to have a shear failure. Let me make a small plot of this just to remind you that how this shear failure happens. If this is sigma 1 and this is sigma 3, and the failure line is this one, what I mean with this equation is that when I am at failure for a given sigma 3, that in this case is going to be Pw minus Pp, the maximum sigma 1 possible is going to be over here. And when I get to that value sigma 1, the rock is going to be at failure. All right. So with this equation, as we said, we can calculate what is the wellbore pressure required to have shear failure. And I hope that you notice from this schematic that the effective radial support Pw minus Pp is going to influence the shear failure, because the higher the value of Pw, the more to the right I'm going to be in this point. Let's say that we are, instead of right now at failure, that we are at a given position like here. If I increase the wellbore pressure, I'm going to move in this direction further away from the shear failure. If I were to decrease Pw, and assuming also that pore pressure is going to remain constant, I'm going to move this way, closer to the shear failure. So the lower the effective radial support, that would mean a lower value of this, the closer you're going to be to shear failure. And there is going to be a minimum value of Pw for which I'm going to be at shear failure, and this is the value that we call Pw shear. When I get to Pw shear, that's going to mean that for that effective radial stress support, I could be at shear failure. So there is something very important to notice here, is that shear failure in the wellbore not only depends on the in situ and initial conditions, like for example the state of stress or the pore pressure or the properties of the rock, but it also depends on the variables that we control in the wellbore. And in that case, that's going to be the wellbore pressure. If we lower the wellbore pressure too much, eventually we're going to get into shear failure at these locations, here and there. And in the wellbore, now let's come back to this drawing, that's going to mean that if I have a shear failure, I'm going to have shear fractures. If I have shear fractures, those shear fractures are going to be oriented at a particular angle of a shear fracture. If you remember, that angle is going to depend on the direction of the maximum stress, which in this case is going to be the hoop stress, sigma theta theta, and on the direction of the minimum principal stress, which in this case is going to be sigma RR, and it's going to be located at an angle equal to beta friction angle divided by 2 plus 45 degrees from the plane of the maximum stress to the plane of the lower stress. And in this case, it's going to result in some shear fractures, which are going to be oriented like this. Now you can imagine that when the failed rocks with this shape next to the wellbore, some of the rock that gets in between the fractures, in this case this one, is going to fall off within the wellbore, and that's going to leave a cavity. So I'm going to repeat the same thing on this plot on the right and have a shear fracture, another shear fracture, and this part of the rock, I'm going to assume that it falls into the rock, it falls into the wellbore, and therefore is not there anymore. Just as a reminder, this is sigma 1, and this one in this case is sigma 3. Let me decrease a little bit the thickness of my pen. Okay, now because I have a shear fracture in this location, I'm going to have a characteristic shape of these wellbores. Here you have one example of how these breakouts look like. In this example, these breakouts are located in this region. You can see some of the shear fracture growing from one side at the characteristic angle from the wall of the wellbore, and also from here. So these are shear fractures, one growing from right to left, the other one growing from left to right. I have another image which is very useful to see how these breakouts look like, and this is an example that we do in the laboratory. In the laboratory, we can utilize a cylindrical specimen like this one that we load, in this case, in vertical directions, and in which we have a cavity that simulates a wellbore. In this case, the load, the maximum load, goes up and down, and there is no stress coming from the sides. So that's why I didn't write sigma 3, but it will be perpendicular to sigma 1. What we see in this case is that as we load this sample and we exceed the value of the shear strength at this point, what I'm going to have is a breakout. This type of shear failure is the one that we were mentioning right here, where the maximum compressive stress, which is now the hoop stress, makes the rock fail in shear at the wall of the wellbore. And this is what you would expect in a wellbore from those shear fractures. All that rock that is not there anymore is the rock that I was telling you before, fell into the wellbore. In real cases of drilling, that will be carried by the drilling mud as drill cuttings, but it's not there anymore. And this is what we call a breakout, a failure caused by shear failure. All right, so let's come back now to the equations that we have over here. And we're going to do one example. This is example 6.1. And in this case, I'm asking you to compute what is this characteristic wellbore pressure and also the mud weight required to avoid shear failure. And that this is going to be the minimum mud weight that I need so I do not have shear failure. So let me interpret a little bit this problem for you. In this case, what I'm going to ask you is that for this problem, you calculate what is the value of PW shear from the equations that you have above, in which we have a vertical wellbore. I'm going to draw the cross section of the wellbore. And we have a given state of stress. Let's say that in this case, as we were having before, SH max is going in north-south direction. This is SH max of 6300 psi, and that we have SH mean in the perpendicular direction. SH mean of 4300 psi. And let me see what else we have in here. This is the side on short. The depth is 7,000 feet. And it doesn't say over here. Oh no, it does say over there, hydrostatic pore pressure. And it has a given pore pressure in the rock. I'm just going to draw it like this. And of course, we have a wellbore in the middle. Okay, so the question is, what is going to be this minimum mud weight for which we are trying to avoid shear failure? All right, so at this point, what I like that you do is that with the data that we have, you pause a video and you try to solve it, and in just a little bit after you're done, I'm going to tell you what the solution is. Okay? All right, so just pause it right now and try to solve it. Okay, so let's see what the solution for this problem would be. First of all, we need to know the state of stress at this particular location. And the first thing that we're going to do is to calculate the pore pressure because we need effective stresses. Here's the calculation of the pore pressure. Since we know that this is a hydrostatic pore pressure, then we use a gradient of 0.44 psi per foot times 7,000. This is the pore pressure that I have. After that, I can calculate my horizontal stresses. And with the properties of the rock, I can calculate what is the friction angle. This is going to be the arc tangent of the internal friction coefficient, 0.6. And with the friction angle, I can also compute the friction parameter Q, which is 3.12 for this particular case. After I have effective stresses and I have the properties of the rock in a way that I can use it, in this case we were given directly what is the unconfined compressive strength, I can calculate the value PW shear, and in this case this is going to be equal to the pore pressure plus 3 times the sigma h max minus sigma h min minus the unconfined compressive strength divided 1 plus Q. And this is the result. This is the pressure in PSI that will be needed um, in order to avoid shear failure. If you had a value of PW of, let's say, 4200 PSI, you would have shear failure. And it will grow a little bit more than just at one point near the wellbore. If you have a pore pressure higher than 4279 psi, then you're not going to have shear failure because you're going to be further away from the shear failure line. How do we compute now the mud weight? Well, what we're going to do is we're going to assume that we have a hydrostatic column of mud weight, and that will mean that there is no managed pressure drilling. For those of you that are working and taking the classes in drilling, we know that sometimes we can modify that pressure in the wellbore if we change the pressure on surface or at the given depth within the wellbore. Well, in this case, we are not going to do that. We're just going to assume there is a hydrostatic column along the wellbore. And as a result, then what I'm going to do is that this pore pressure that I have calculated, I'm going to scale it according to the depth the current depth that I have, and that's going to give me a gradient in psi per foot. And then I'm going to convert that to the equivalent in pounds per gallon by multiplying this by the gradient of water in pounds per gallon divided the units that I have over here, also for water, in psi per feet. So once I do that, these units are going to cancel out, psi per foot. I'm just going to have the value in pounds per gallon. So notice that this number is going to be uh, less than 1, but it's going to be bigger than 0.44. And once I divide this number, which, let me compute, I have a calculator right here, 4279 divided 7,000, that gives you 0.61. When you divide 0.61 divided by 0.44, that gives you a number higher than 1. And when that number higher than 1, you multiply times 8.3, that gives you 11.57 pounds per gallon. So what this means is that your mud weight, in order to achieve this pressure at this true vertical depth of 7,000 feet, has to be 11.57 pound per gallon. If you have that mud weight, you're going to have this pressure. If your mud weight is lower than this pressure is going to be lower and you're going to have shear failure. If your pressure is higher than this, if your mud weight is higher than this, then your pressure is going to be higher too, and you're not going to have shear failure. Okay, but now, is shear failure, do we have to avoid always shear failure in wellbores? The answer is no. A little bit of shear failure is fine. And in fact, sometimes we calculate what is the shear failure and we allow a shear failure in a given extent so that it doesn't compromise the stability of the wellbore. And so as a parameter of design, we can allow a given breakout angle or a given area where we do know that it's going to be shear failure, and to keep this small enough so it doesn't compromise, as I was saying before, the stability of the wellbore. So then the question is, how much is or can we allow a breakout to be in terms of angle so that the wellbore is stable? Well, that's more or less it's a difficult question, and it's going to depend on the rock type. But in general conditions, we could say that the breakout angle lower than 45 degrees, sometimes 60 degrees, is going to be reasonable, and it's going to result in, even though there is shear failure at a particular location, that's going to result in a stable wellbore. Okay, so in this case, then, if we want to calculate a breakout angle, and let me come back over here, this is going to be the angle for which I'm going to have shear failure, and it's going to happen not only at a single point, exactly 90 degrees, or at 270 degrees, but it may go over a region which is a little bit larger. In this example that I have here on the left, what I have is in red the region in which the hoop stress, in this case, is calculated with these boundary stresses, sigma h max and sigma h min. And here in red, I have that hoop stress without any effective radial stress support. And what you should see from this image is it shows where those stresses are the maximum and how that varies going away from the point of the maximum stress. So, for example, in this case, if I if I were to say that the maximum unconfined compressive strength of the rock is 30 MPa, that means that all this area will be at failure. And in this plot, that would mean that all these areas with dark red uh, would be at failure, and I would expect failure in all this region. And as a result, all of this is going to be under shear failure, and that's going to make a breakout in this location with an angle that is going to be higher than 0, because it's not only just one point which is failing at this location here or there, it's all this entire region. Okay, so if I wanted to do that, what I would have to do is there is a simplified approach in order to calculate this breakout angle, and the simplified approach consists on looking at the cross section of the wellbore and determining the condition of failure at the beginning of the breakout. So in this particular case, this is the breakout, or the region where I'm going to have shear failure. This is going to be the point in which I am at the condition of shear failure, exactly sigma 1 equal to UCS plus Q sigma 3, and all other regions do not have shear failure. All the area which is within the region in which there is shear failure, which is in between this point and that point, that's going to be the area of the Wellbore breakout, and this angle going from there to there is going to be the breakout angle. Okay, so how do we determine this value? We use the equations of Kirch. In this case, we have left the component theta available to calculate what is going to be the condition of stress at a given angle theta from the direction of the maximum stress. And what I'm going to do is I'm going to set sigma 1, the maximum stress, as sigma theta theta, and sigma RR to be the minimum principal stress, sigma 3. When I do that, this is the equation. Let me expand it a little bit. It's a long equation. What you have in brackets is sigma theta theta, which in this case is sigma 1, UCS times Q, effective radial support, which is the same as before, PW minus PP. And after you work with this equation, you can solve with what this angle theta is, which is going to depend on the condition of the stresses and also on the effective radial stress support, which is in turn a function of the mud weight, and you can also determine what the breakout angle is. So in this case, if I were to give you a wellbore pressure which is a certain value, you could calculate what is the breakout angle in which this wellbore pressure is going to result. The lower the wellbore pressure, the bigger the breakout angle. The higher the wellbore pressure, the smaller the breakout angle. And if PW in this equation is equal to the same PW shear that we calculated before, which is here in equation 6.9, the breakout angle is going to be equal to 0. But that is going to mean that there is failure just at a single point at theta equal to 90 and theta equal to 270. Okay, so here you have the same equation, and instead of calculating what is the breakout angle for a given pressure, I'm reversing the problem, and what I'm doing is I'm setting what is my breakout angle by design. For example, 60 degrees. I could say in a place I'm going to allow a breakout angle of 60 degrees, and by inputting that breakout angle, I could calculate what is the wellbore pressure required, or the resulting wellbore pressure for that given breakout angle. Again, if I were to increase the breakout angle, then this wellbore pressure is going to be lower. If I were to decrease this wellbore breakout angle, then this pressure would be higher. All right, so in this second example, I'm taking the same case, but now what I'm doing is I'm calculating what the breakout angle is going to be for a mud weight, which is 10 pounds per gallon. If you remember from the previous problem, the solution was that PW shear was caused by a mud weight of, let me see what the solution was, 11.57 pounds per gallon. So if I were to drill with a lower mud weight, I would expect the breakouts to be more than just a tiny point, but to have some angle. And that's what I'm doing in this case. I'm using that, let me erase this. This is actually the density of the mud. In this case, I'm saying that if the density of the mud is equal to 10 pounds per gallon, smaller than the value of PW shear, the question is, what is going to be the breakout angle? And I know that it's going to be higher than 0. So if you work through the problem, just, again, you may want to pause the video now, work with your solution. The answer is given by these two equations, 612 and 613. You have all the data that you need over there. The only thing to do will be to calculate PW using that mud weight. But other than that, you have everything. Okay, so please just go ahead and try to obtain this breakout angle from these two equations, and then we'll check the solution. Okay, as I was telling you before, the first step would be to calculate what is the pressure exerted by a mud with weight of 10 pounds per gallon. In order to convert this to PSI, I'm going to convert this gradient to PSI per foot using the conversion from water, and you multiply that gradient times 7,000 feet, and the result is going to be PW. After you do that, you utilize the equations that I was telling you before. In this case, I have combined those two and put in all the values of sigma h max, sigma h min, what is the friction coefficient of the rock, the friction parameter Q of the rock, what is the UCS and the pore pressure and all of that. This is my result, 66 degrees. So in this case, if I were to use this mud weight, I would obtain a Wellbore breakout angle of 66 degrees. Again, let me summarize this. And for this particular case, I'm going to follow this convention, or well, it's not actually convention, but I have assumed in this problem that I have SH max acting in direction north-south. I have the wellbore. In this case, that would mean that my breakouts are going to show up in the two locations that where I'm going to draw right now. So this is going to be the maximum stress going, in this case, let me put some additional axis here just to make it clear. This is the north, This is a cross section of a vertical wellbore, remember? So this is going to be the north, this is going to be the east. Here, let me shorten this a little bit, so just to make it clear that this is going to be SH min, and this is going to be SH max. As a result, as I have calculated in this case, my breakout angle is going to be 60 degrees, which is going to mean that I'm going to have breakouts which are 66 degrees wide in these two locations. So this is going to be the breakout. All that rock that I'm drawing over here in red that's going to fall into the wellbore is going to leave an empty space, and this is going to be the breakout angle WBO, which in this case this is going to be 66 degrees. In the previous case, if I just use PW shear, the shear failure is just going to be a tiny point over there with a breakout angle equal to a value close to 0. By lowering the mud weight, what I have done is I have increased what that breakout angle is. Okay, so this is how we determine what is the minimum pressure required in order to avoid shear failure, PW shear, and if we allow for some breakout angle, we can lower that mud weight. As we have seen before, this is going to be the shape of those breakouts, and you know, in this case, this is real rock. This is a real picture of a small wellbore done in the laboratory, but this is going to be what you should expect as the breakout shape. Well, let's take a look at those in the wellbore. In the wellbore, we cannot take direct pictures. Sometimes you can run a camera, but it's a lot more useful to do what are called formation images, or to run a formation imaging tool. Those tools, they can use either ultrasonic wave, like in this case, or electrical resistivity. And basically what you do is you measure all around the wellbore. Imagine that we have, in this case, this is our wellbore. All around the wellbore, well, let me do it actually with my other example. Let me take this out of here. And here we have a wellbore image, okay? And this is our wellbore. What we do is, as I was saying before, to run a tool that measures properties of the wellbore all around the wellbore in an angle of 360 degrees. And we can either measure ultrasonic P wave or electrical resistivity. In the case of the ultrasonic P wave, what you do is you send a wave from the center of the wellbore, and you send it to the wall of the wellbore, and it bounces back and tells you how long it takes for that wave to come back. And when you have a breakout, it's going to take longer for that P wave to bounce back in the rock and come back. And in this plot, longer time is going to mean a darker color, which are these dark regions in this image. And if it comes back in a shorter time, that's going to be a brighter color, which in this case is going to be all this region. So in this case, just please concentrate on these wide regions that look like track wedges on the pavement. These are going to be the breakout. This is how a breakout looks like in these formation imaging tools. And notice that this is an angle that goes from 0 to 360 degrees, in this case from north through east, and then to the south, and then to the west, and then back to the north. This is what is called an unwrapped image of a wellbore, because the wrapped image will go from, in this case, from the north, east, south, and west and north again. And if you were to open this into a plane, that's what we see over here. It's the unwrapped image, and the location um, of these regions tell you where the breakout is. So in this particular example, the breakout is a little bit lower at the position of the east. And notice that also we have two regions, which means that we have two breakouts. Here in the image on the right, we see just one breakout, but there is also another one in this area that we cannot see because of the angle in which we was taking the picture. But we would also expect a similar breakout on this side. In this particular experiment, what happened is that shear fracture propagated a little bit longer into the rock, and that's why you see this larger fracture over here. But in this side of the wall, there is a similar breakout, and that's what you will see in wellbores as well. One more thing to notice over here is that from these images, you could measure what is the angle of the breakout. For example, we know that from north to east there are 90 degrees, and for example from here to there this is going to be 45 degrees. So around this location the wellbore breakout angle is 45. In some other regions, like for example say here, from here to there, it appears more like 60 or 70. And although we have a breakout in this case, you can see that the wellbore is stable. Otherwise, this image would not be possible. You wouldn't be able to run a wellbore tool through a wellbore which is open and it is not stable. A similar image can be obtained also with electrical resistivity. This is another type of another property of the rock that can tell you the presence of breakouts. Here it's a little bit more difficult to analyze where the breakout is. In this case, I'm going to open up here the figure also to show the reference of this work and give credit to the original image. The breakout is right over here, and what you see with these wide black lines is regions that could not be scanned by this electrical resistivity tool. In the case of the electrical resistivity tool, we do not get data all around the 360 degrees, but just in the areas where the electrical resistivity paths touch the wellbore. This is a tool that is used to image wellbores. And you can see that these are the paths in which you have the electrodes that measure the resistivity of the rock. And there are some regions in which these paths are not going to touch the rock. Those are those regions in black for which we do not have data. But in this case, I hope that you can see that around this region we have a breakout. Those areas with darker color mean that the resistivity of the formation is higher, and that means that there is a wellbore at that, there is a breakout at that particular location. Where the image is brighter, that means that we have rock that has not been failed. And when we put all this together into a wrapped version of the image, this is what we observe. For example, in this case, this image corresponds to this image over here, where the breakout is a little bit lower than at the position of the east. So here the east, the breakout is a little bit further than 90 degrees. So if we go 0, 90, here's the breakout. We continue, go to 270, which would be the west, and here the breakout appears again, which is that region. And by measuring where the rock has failed and the diameter of the wellbore increases, that's going to allow us to measure also from these images what is the wellbore breakout angle. And very importantly too is that from these images you can also tell what is the direction of the in situ stresses. In this example of a vertical wellbore, we will always expect to have the breakout angles oriented at a characteristic orientation with respect to the maximum stress. If the maximum stress is going in this direction, the breakout angles are going to be in perpendicular direction right over here, here and there. So if we know the orientation of the breakout angles, we know what is the orientation of the stresses that cause those breakouts. Okay, so uh, this is a discussion about breakouts, how you determine breakout angles, how you determine the mud pressure and the mud weight for a given breakout angle. And there is one more application for this. In some cases, when you drill a wellbore and you know the properties of the rock and you know the breakout angle, you can also solve for what is the maximum principal stress at a particular location. We have seen that computing the value of vertical stress is relatively straightforward. Computing the value of minimum horizontal stress can be done through hydraulic fracture tests in case of normal faulting and strike slip regimes. But calculating the value of the maximum horizontal stress sometimes is something which is quite difficult, and there is quite a bit of uncertainty in order to do that. This is one method that you can use in order to calculate SH max. Again, if you know the conditions such as the pore pressure, the minimum horizontal principal stress that can be calculated from the hydraulic fracture test, if you measure what is the breakout angle and you know the properties of the rock, UCS and Q, that you could determine in the laboratory, you could determine what SH max is. Okay, this finishes the discussion about breakouts.